Hello, everyone. This is the Unit 3 Calculus seminar on the addition and subtraction of vectors. Just to review what you learned in the introduction seminar, let's label the following vector. At the bottom of the screen, you can see my arrow pointing to it. You'll notice that the starting point of the vector is referred to as the tail. Hello, everyone. This is the Unit 3 seminar on addition and subtraction of vectors in calculus. Now, if I can draw your attention to the vector that I've drawn at the bottom of the screen, my arrow is pointing to it. From the introduction seminar, we learned that you label the starting point of the vector, that is referred to as the tail of the vector. And where you see the arrowhead, the ending point of the vector, is referred to as the tip, or sometimes as the, oops, I think in your textbook, it is referred to as the head of the vector. So we have the tail and the tip, or the head of the vector. So please refer to those terms when we are talking about addition and subtraction. Now, the first part, if you have two vectors acting in the same direction, the overall magnitude is equal to the sum of the two individual magnitudes. And you can see that the resultant is moving in the same direction. So in this case, we say the resultant, we're adding vector A plus vector B. We're moving in the same direction. But if you have two vectors acting in opposite directions, this often happens with navigation problems. And today we're going to refer to a plane problem where a vector is moving in an opposite direction. The overall magnitude is equal to the difference of the two individual magnitudes. So we have vector A. Vector B is moving into the opposite direction. So you might look at the equation and it looks like a subtraction of vectors, but what we're really talking about is vectors moving in opposite direction. So the resultant is this portion over here. When you add two or more vectors, you're finding a single vector called the resultant. Those of you who have already learned physics have dealt with working with vectors in component form and solving for the resultant. The resultant often refers to our solution that we're looking for when we are adding two vectors. We're trying to figure out what is the result of adding the two vectors, and that is what the resultant is. For example, if you walk north 800 meters, this is my first vector, walking north, then west 600 meters. The result is the same as if you walked, if I'm talking about my resultant, north 37 degrees west for 1,000 meters. The resultant is often represented by the symbol R. For example, in a tug of war, 4 people pull to the left with forces of 100 newtons, 87, 95 newtons, and 102 newtons. The total force, when you add them up, is equal to 384 newtons to the left. So we're going to look at some application problems with vectors. But first, I want you to pay special attention to copying in your notes the methods, the step-by-step rules for the different methods. The most popular method is the head-to-tail method. So if I have these two vectors, u and v, part A, I'm going to explore two methods for adding the vectors, and then looking at combining when we have vector u and we're looking at the opposite vector, vector v in the opposite direction. That can look like subtracting vectors. So for method 1, use the head to tail method. So we want to translate, sorry, just want to make sure the volume is up. We want to translate vector v so that its tail is at the head of vector u. We can also say the tip of vector u. So vector u is my first vector. I'm drawing that. And at the very tip of vector u, you want to start the tail of your second vector, vector v. And this is how you want to arrange vectors that you're given in a word problem. Now, the resultant that happens when I was taking calculus in high school, my number one question was, how do I know how to draw the resultant? And this equation, when you're using method one, kind of summarizes how you should always know what direction you should draw the resultant. So the resultant, you're going to go from the tail of the first vector. Here's my vector u. I'm going to go from the tail of my first vector to the tip of or head of my second vector. And that resultant represents the sum of vectors u and v. So I have the tail of the first vector to the tip of the second vector. And that is method number one. Method number two is the parallelogram method. Grab my marker here. And we want to translate with the parallelogram method. I'll highlight that. Oops. Try again. Use my straight line tool. There we go. For the parallelogram method, and switch the color, we want to always make sure that we are translating our vectors so that they are tail to tail. Both their tails should be touching. Then we're going to construct a parallelogram using vectors that are equivalent to u and v. Our very first application problem, we're going to be copying and transposing vectors that are equivalent. The resultant is the indicated diagonal of the parallelogram. So the diagonal that's moving from the tail of the point where the two vectors meet to the tip or head of where the equivalent vector is going to intersect. So using the head to tail method, if we go back to vector one, we can also illustrate subtraction. So when I'm talking about subtraction, I'm talking about vector u plus negative vector v. So if this is vector v, let's grab my circle. If this is vector v, negative v is going to be moving in the opposite direction. So this vector over here is moving in the opposite direction, but we're still using the head to tail method, meaning the resultant is from the tail of the first vector to the tip of my second vector, even though the second vector has been transposed or illustrated in the opposite of direction. For the parallelogram method, I'm still using
Ms. Marino, contact the office, please. Ms. Marino.
I'm still using the vector in the opposite direction, and we're still completing the parallelogram. What I'm talking about with equivalent vectors, so if this is a vector u, the equivalent vector for vector u is going to be over here. And the resultant goes from the tail of vector u to the tip of the equivalent opposite vector to v. This is a little bit harder to see, so we're going to actually do this problem starting from scratch. For subtraction using the tail-to-tail method, we translate vector v so that u and v are tail to tail, and we draw a vector from the head of vector v to the head of vector u. This is actually method number three, the tail-to-tail method. Oh, I want to do that. So this is a whole new method. We call this new vector vector w. So vector w is equal to the opposite vector of v added to the original vector u. We can rearrange that to illustrate vector u minus v. And u minus v can be drawn from the head of vector v to the head of vector u when u and v are placed tail to tail. There's so many different methods we can use. The tail to tip method, yes, tail to tip method is the most popular. And we're going to be using that for the more difficult problems today. Question number one, given that angle A and B, sorry, given vectors A and B such that the angle between, I want to underline and really emphasize that today. The angle between the two vectors is 60 degrees. Angle vector A, the magnitude of vector A is equal to 3. The magnitude of vector B is equal to 2. We want to determine the resultant, which is the sum of vector A plus B. And before we start, I just want to go back to here. I do know the magnitude of vector A and B. And where students often go wrong is they think that they're plugging in the angle of 60 degrees into the formula. Now, when I'm talking about the formula, remember that in order to solve for the resultant vector, I need a magnitude and a direction. In physics, when you're learning vectors and you're solving with components, you're often working with 90-degree angles, and we stick to Pythagorean theorem. I really encourage physics students to please, when you're doing calculus problems, try not to stick to the component method, because then you're not illustrating the full solutions we are looking for. In our solutions, you're looking at the information given and you're trying to figure out, when you're solving for your, especially for your direction and sometimes for your magnitude, you're comparing what you are given in the problem. So whether you are given two sides and an opposite angle, one side and all angles, the sine law is expressed if you want to solve for an angle. The cosine law is the sine law is used when you have one sine and all angles if you're looking for a side. So this chart right here and these situations have to be memorized for the test. Very important. We're not going to be giving you this information on the test. And based on the word problems, you have to know when to use which formula. So the cosine law is used quite often when you are solving for a third side. You want to make sure that you have two sides in a contained angle when you're using the cosine formula. Or the easiest one to remember is if you know all three sides and you're solving for an angle, that's the other situation where you're using the cosine law. So back to the parallelogram method. In order to, because I can clearly see my vectors are, we're solving this with the vectors, their tails together, because and the tails have to be get together because the question is giving me the angle between them. What I can do is take the equivalent vector from V. So, right, I want to translate my vectors so that they are now tip to tail, tip to tail. So I have my vector A, my vector B started off here, but right now they're from tail to tail. I want to take the tip of the first vector, and that's where I'm going to place the tail of my second vector, right? I can do the same thing with vector A. Vector A, I can move, and turn it into a different color, maybe green, and I can kind of transpose vector A here. Okay, so now that I've formed a parallelogram, now the resultant, I'm going to make the resultant in a nice bright purple. The resultant, if I go back to the formula I wrote before, the resultant is we draw the resultant from the tail of the first vector to the tip of the second vector. So now that I've transposed my vectors, I start at the tail of the first vector and I'm moving to the tip of my second vector. I'm going to draw a little arrow to match, and this is going to be my resultant vector. Okay. Now, to solve for this, the magnitude of this resultant, because remember here, the lines outside of A plus B means that I'm solving for the magnitude. So my resultant is equal to vector A plus vector B. And I have to put the magnitude symbols outside. Let's change my colors here. I know the magnitude of A is 3. And the magnitude of B is 2, right? So I have two side lengths. So if I go back to my trig formulas, I have two side lengths. And if I know the contained angle, that tells me that I can use cosine law. And to use cosine law, let me just reveal the formula here. I need the magnitude of A plus the magnitude of B squared, A squared plus B squared, minus 2AB. And you'll notice that I did not put cos 60. That is a common error that students constantly do. The 60 degrees was over here. This is equal to 60 degrees, but I need the contained angle between these two vectors because this is the triangle I'm solving for. My resultant over here, my vector A, vector B, so I cannot use 60 degrees. So if I extend, I'm going to use my drawing tool and extend this straight line. If the angle I was given is 60 degrees, then this angle, which is also equivalent to this, so that's why I'm using the green, that would be 180 minus 180 degrees minus what I was given, 60 degrees. And that gives me a contained angle of 120 degrees. Okay, so that 120 is what I'm substituting into the cosine formula. And want you to pay special attention to the fact, oh, I think I can just move this. So I'm going to move that up there. And that way I can erase what I wrote. There we go. Pay special attention to the fact that I'm not just going to substitute the magnitude of 3 and 2 into the formula. I first substitute everything into the formula, and then I'm going to show some steps. Steps are really important because even if I miscalculate and get the final answer wrong, if I show that 2 times 3 times 2 is 12, cos 120 degrees is negative 1/2, 3 squared plus 2 squared is 13. I'm showing some step that allows your teacher to give you some part marks, even if you get the question wrong. Now, to go from the magnitude of A plus B squared to the magnitude of A plus B, which is what I'm looking for, the magnitude of the resultant, I have to actually take the square root of 19. And then you want to show that step. So that tells me that the magnitude of A plus B is equal to the square root of 19. They didn't ask me for my direction vector. They just asked me for the magnitude for this particular question. But for many questions, you're going to have to solve for the magnitude and direction. So let's take this navigation problem. I think we're going to encounter two navigation problems, a difficult one, and this is more of an easy version. This particular navigation problem is going to form a 90-degree triangle, which makes it easier. So whenever you're doing word problems, it is important to real world problems, it's important to state what each vector represents. An airplane heads due south at a speed of 300 kilometers per hour and meets a wind from the west at 100 kilometers per hour. What is the resultant velocity of the airplane relative to the ground? So first of all, we're going to let vector v represent the velocity of the airplane without the wind. So I can see that vector v, if I use my highlighting tool, vector v is heading south like this. Okay, the airplane without the wind would just continue to travel south. However, the wind is pushing that plane from the west, right? So let W represent the velocity of the wind. The wind is pushing that airplane from the west. It's coming from the west, so it's pointing the tail starting starting at one point, but moving in the direction from the west. That's actually pushing the plane a little bit more east. So what the resultant actually represents, let R represent the resultant velocity of the airplane with the wind. So the velocity of the airplane with the wind taken into account relative to a fixed point on the ground. So this is the actual path that the plane is going to travel. I'm going to say that again. The resultant represents the path that the plane is going to travel. So even though the plane wants to head south, the wind is pushing it towards the west so that the actual path that the plane travels is in this direction. And I know right away from the diagram that that direction it's headed southeast. I want to keep that into consideration when I'm stating my direction later on. Okay, first part of the problem, the magnitude of the resultant. I want to underline that. So the magnitude of the resultant speed. In order to calculate that resultant, I'm going to use the Pythagorean theorem because I have a 90-degree angle. So I have the r squared is equal to velocity of the airplane squared plus velocity of the wind squared. I already know from the problem the speeds. Go back to here. The speeds. Oh, let's see if I can zoom in a little bit more. Okay. So the speeds of 300 kilometers per hour represents the magnitude of the airplane without the wind, and 100 represents the magnitude of the wind. So if I zoom at 125, yeah. So I'm going to actually label the speed is the magnitude. Velocity of the airplane is 300 kilometers per hour, and velocity of the wind is 100 kilometers per hour. If I use the Pythagorean theorem, I get 100,000. And if you take the square root, so the square root of 100,000, you get 316.23, and that represents kilometers per hour. So that is the magnitude of my resultant right here. Now, when I'm trying to solve for the direction, because remember, every solution needs a magnitude and a direction of when you're solving for vectors. So the direction, I am The angle that I'm solving for is always the starting point, happens at the starting point of my resultant. My resultant is in this direction, so the starting angle is over here. So when I'm labeling my triangle according to this starting point angle theta, then the 100 is actually going to be my opposite. And the 300 represents my adjacent. So when I reduce that fraction, I have tan theta is equal to 100 over 300. Angle theta, don't forget the angle theta is equal to the tan inverse of 1/3. Angle theta is equal to 18.4 degrees. But it's not enough to just state the angle. The direction also needs, you have to put a bearing: north, south, east, west, northeast, southeast, northwest, southwest, that sort of thing. So every word problem needs to have a statement that contains the specific direction. So that plane in this particular question is heading south 18.4 degrees east at a speed of 316.23 kilometers per hour. Okay, before we move into more difficult navigation question, when I said before, it's going to be very clear. There we go. To erase. Yep, here we go. Okay, so this is not a plane navigation problem. In your word problems, just like with the last one where we had the plane first, that was our first vector. The second vector was the wind that was coming from the west. It's always going to be clear which vector is your first vector, which vector is your second vector. So in an orienteering race, you walk 100 meters due east. So this vector, AB, is drawn 100 meters heading due east. And then we walk north 70 degrees east for 60 meters. This vector is my second vector. The first vector where I'm walking due east is the first vector. The second vector, I have to walk north 70 degrees east. This is a little bit trickier because at the end, the tip of the first vector, I have to start my second vector, but I have to start from the north. So you're going to draw this diagonal down. And we learned in the last class about bearing. So from north, 70 degrees towards east, I have to draw this second vector, start drawing the second vector, right? And I'm going to draw that vector for 60 meters. Now, you cannot, think about your scale. You cannot draw the 60 meters with the same length as 100 meters. You have to keep the scale in mind. Also, angle B is not, when I'm looking at this diagram as a triangle, as a whole, because my resultant is going to be drawn from the first vector, the tail of the first vector to the tip of the second vector, I am going to form a triangle. So it's important to note that the angle B, when you drew this horizontal north, imaginary north line, and then calculated the bearing, on the other side from north to west, that forms a 90-degree angle. Okay, so 90 degrees plus 70 degrees means that my total for angle B is 160 degrees. Before I've even performed any step, when you're drawing your triangle, you're really trying to pay attention to what this information that you're given is going to imply about your triangle diagram. I just kind of also want to make this a bit bigger so you can see that better. Okay. Now, what else are we given? We are also want to keep in mind that our resultant is moving in the direction starting at angle A, ending at angle C. So because I've calculated this 160 degrees, and I know my magnitude, which is 100 meters due east and then 60 meters northeast, I have two sides, just like in the first question, two sides and the contained angle, which is 160 degrees. So I'm going to start off using cosine law, right? I'm labeling the vectors as AB, BC. So I have AB, the resultant, the magnitude of my resultant is AB squared plus BC squared minus 2AB BC cos 160 degrees. When you substitute your values, 100 for AB and 60 for BC, and be very careful you don't confuse that 60 with cos of 160 degrees, which is the contained angle. I'm going to go ahead and write that down too, so you don't forget that that is the, oops, make the font smaller, contained angle. Bigger. Okay. I want a step now when I'm combining and solving for the magnitude. So I know that my magnitude, and I'm going to go ahead and write that in, is 157.7 meters. But I also have to solve for this direction. I've written the answer right here, but how do I find this angle? Let's call it angle theta, right? The angle, make that a bit neater. So I'm solving for angle theta. My starting angle in this triangle that I've drawn, which is going to help me calculate the direction. Okay, so because now I know all three side lengths and I'm solving for this missing angle, I can actually, and I do know this contained angle, the ratio of sine B over B. I can use sine law. I'm going to set it off as I know the resultant and I know the angle that is opposite the resultant. So 157.7 over sine 160, and I'm going to set up a ratio of what I don't know. So I don't know the angle A, sine A, over 60. So you can go ahead and cross multiply or you can rearrange. So sine A is equal to 60 times sine 160 divided by 157.7. I would actually include another step in here. So angle A is the sine inverse of this ratio that I set up. If you punch that into your calculator very carefully, you would determine that angle A is 7.5 degrees. But remember, the question, if I get your attention to come back here, the question is, how far are you from your starting point? We already know that 157.7 meters, but at what bearing? So bearing is always calculated from the north to this resultant angle. So because this entire from north to my first vector is going to be equal to 90 degrees. I actually have to calculate 90 degrees in order to calculate bearing. 90 degrees minus 7.5 degrees. And that's going to be equivalent to 82.5. 90 minus 7.5 is 82.5 degrees. And because I'm traveling from the north towards the east, the bearing is north 82.5 degrees east. So 90 minus 7.5 degrees is 82.5 degrees. We're coming from the north to the resultant. That would be north 82.5 degrees east at and the distance traveled is 157.7 meters.